So the main idea about systems in equilibrium is that they are not static, they are dynamic. They are constantly responding to disturbances. So let's say that you have a chemical system and you end up having a disturbance. So either the reactants decrease, for example, or you add in reactants, so those increase. Those are typical disturbances. And what will happen is that the system will return to equilibrium by counteracting that disturbance. So anything you do to change it, it'll go back to establish that equilibrium. It'll do something to establish that equilibrium, to go back to equilibrium. So here we have that same analogy about the countries and people, moving back and forth. So here, let's say equilibrium is disturbed when the population in country B grows. So all of a sudden it just increases a lot. So how does the system respond to this? It will respond to minimize disturbance. So you can see how before there was like 2 people coming in, 2 people going out. Now we have 4 people going out, 2 people coming in. So we're increasing the amount of people leaving country B because we had that original increase in country B in the first place. So what this is Le Chateliers Principle. So whenever a system that is at equilibrium is disturbed, it will return to equilibrium by counteracting that disturbance. So Le Chateliers Principle lets us predict the effect of various changes in conditions and what those changes have on the position of equilibrium. So we learned about Q and K. Q is the reaction quotient at any point in time. K is specifically the reaction quotient at equilibrium. So it's the concentrations of the products divided by the concentration of the reactants at equilibrium. Now, normally nature wants Q to equal K, like reactions will want to be at equilibrium, so usually Q will equal K. But in cases where, equilibrium is disturbed, so let's say Q is less than K, so for whatever reason, the reaction was disturbed, and now you have a Q value because whenever you disturb the equilibrium, the concentrations are going to change, meaning you no longer have K, like you're not calculating K, you're calculating Q because it's at a different point in time. It's not at equilibrium, or a different point in the reaction, not in time. But let's say you have a Q less than K. So just to visually show you this, here we have Q less than K. What will happen is the forward reaction will proceed in order to form more products to reestablish that Q, make it larger, and make it equal K. So when Q is less than K, your reaction will go forward to form more products and reestablish equilibrium. When Q is greater than K, nature will make the reaction proceed to the products. So here you have Q greater than K, meaning you have a lot of products, too much. So you will move the reaction that way to make that number be lower, and then it'll match K if this is the response. And obviously when Q equals K, the reaction as it is at equilibrium, and this is overall what nature wants, so that's why these changes occur. And overall, this is the idea of Le Chateliers principle. So we have several different changes that can occur to equilibrium, and we are going to look at the effect of these changes. So first of all, we have the most simple type of change, which is concentration change. So let's say you have this reaction, and this is the same one we've been looking at over and over. We have N2O4 gas turning or decomposing into 2NO2 molecules, gaseous molecules. So let's say you add more NO2. You are increasing the amount of product, right? So you're adding NO2, you're increasing the amount of product. Equilibrium is now disturbed. You increase the concentration of NO2, and now the system is going to try to fix that change, right? It wants to reestablish equilibrium. So what's going to happen is the reaction will shift left to form more N2O4 because you had all that extra NO2, and it will reestablish equilibrium in this sense, in this way. So when NO2 is added, some of it will combine to make more N2O4 to counteract that disturbance. So let's look at this graph that also illustrates this change in equilibrium. So again, we have the same reaction, and we have certain concentrations of them at equilibrium, right? You have a certain concentration of NO2, a certain concentration of N2O4 at equilibrium. And at equilibrium, Q equals K still. And let's say you increase, so this right there, that is an increase in NO2, which is what we just said was happening to the system. So you see this increase, and you disrupted the equilibrium, and now Q does not equal K anymore. It is not at equilibrium. So what's going to happen is, to counteract that, this will begin to decrease because more of this N2O4 will be formed. So the reaction shifted to the left because you had that increase over here, and now you have more N2O4 being formed, and now equilibrium is reestablished. Let's look at the opposite situation. So again, you have certain concentrations of both of these, of the reactant and the product, at equilibrium, Q equals K. Let's say you add in N2O4. So this time we're adding and increasing N2O4. What is going to happen to the reaction? It is going to shift this way to counteract this disturbance. So we increase this, the N2O4, it went from this concentration to this concentration. And to counteract that change, we are going to increase the amount of NO2 being formed. So it shifts this way, NO2 starts forming, this decreases, and you reach new equilibrium concentrations. And now Q equals K again, equilibrium is reestablished. So we looked at how concentration changes can affect equilibrium, but bear in mind these reactions we've been looking at have been gases. They've been homogeneous equilibrium systems that are, all gas. So another thing that can happen is that you can add more gas, right? Just like how whenever we were looking at just in terms of concentration, when we're adding more gas, we are also affecting pressure. So remember, gases exert certain amounts of pressure. What happens when this pressure is increasing? So whenever you add gaseous reactant, this increases partial pressure. This will cause equilibrium to shift to the right. So if you increase, so again, we're looking at this reaction, and these are both gases. We're looking at this reaction, and let's say we increase the reactant, meaning N2O4, we increase that. What will happen to the reaction? It's going to shift to the right in order to counteract this increase in pressure. So increasing partial pressure also increases concentration, so it's along the same idea, obviously, of concentration. So that's why it'll shift to the right. If you add an inert gas, meaning a gas that won't react, so like helium, neon, argon, these gases will have no effect on the position of the equilibrium because they do not affect the partial pressures. So we looked at the effect of adding a gas that is part of the reaction. It'll basically increase the concentration, and it'll increase the partial pressure, and it shifts how we normally see equilibrium systems shift. What if you decrease volume? That's another parameter that you can change for gases that really change everything else about them as well. So what if we decrease the volume? So if we decrease the volume of the container, it increases the concentration because you have a lower overall volume. Remember that concentration molarity is mole per liter. Liter is a volume. So if you're decreasing the volume, you still have the same amount of moles. So if you're dividing by a smaller number, you will get a higher concentration. Brackets mean concentration. So decreasing volume increases concentration. It increases the partial pressures, and if the partial pressures increase, then the total pressure in the container also increases. So it might kind of seem like it doesn't tie together, but it does. Gases, all of their parameters, they follow the gases we're talking about, follow the ideal gas law. So if one thing changes, it has its relationship to the other parameter. So volume and pressure are inversely proportional. So when you decrease volume, you will be increasing the pressure. So think of it, you're making the overall container smaller. So the gas has less space to, hit on the sides of the container. This increases the pressure. So when the volume decreases, the equilibrium will shift to the side with the fewer gas molecules. And I'm going to show you on the next slide what we mean by this. So another Thanos meme. I don't know why there's so many Thanos and like chemistry memes. I don't know why it's a thing. I didn't make these up. I found them, but when pressure is, for example, decreased, so this is the opposite of what we're saying here. So when volume decreases, pressure increases, but here pressure is decreasing. The equilibrium will shift to the sides of more moles of the gas. So this is the other situation in comparison to this one. And here I'm actually showing you a better picture and how to visualize this. So let's say you have this particular reaction. We have N2 reacting with hydrogen to give ammonia. So on one side of the reaction, the reactant side, we have 4 moles of gas. On the product side, we have 2 moles of gas. And we're getting that from the stoichiometric coefficients. So we're just adding those coefficients up. So let's say you increase the pressure. What is going to happen to the reaction? We are going to shift to the side with less moles. So you are increasing pressure, and this is overall causing, less space. There's a smaller volume, right? We're decreasing volume in this case. We're gonna readjust to that disturbance by shifting to the right, which is the side with the fewer moles of gas. Let's say you decrease pressure, meaning you're increasing volume. So here you're increasing volume, here you're decreasing volume. Remember, volume and pressure are inversely proportional. So here you decrease pressure, increase the volume, and we still have the same reaction, N2 reacting with H2 to give NH3. And this time we're going to shift to the side with more moles of gas, because now we have more space, so we can fit more moles. And this just summarizes exactly what we were just talking about. So this is a really good visual of this effect of volume on equilibrium of a gas system. And here I have the same image we had earlier when we were just discussing heterogeneous equilibrium systems. So what effect does removing or adding a liquid or solid have on the equilibrium, and how does, Le Chatelier's principle tie into this? So adding or removing a pure liquid or solid has no effect unless all of the liquid or solid is removed. So for the most part, if you add liquid or solid, it's not going to do anything to the overall reaction. So remember how here we started off with a certain amount of carbon, here there's more, but overall they're still at equilibrium. It doesn't matter. And remember that we don't include liquids or solids in the equilibrium expression, and that's why they don't have any effect on changing the equilibrium. So another effect that we can look at and how it affects equilibrium is temperature. So for these reactions, they either have to be exothermic or endothermic. So let's say we have an exothermic reaction. Exothermic reactions give off heat. So heat we can consider like a product. If we increase the temperature, it's like we're adding in more heat, which is a product. So according to Le Chatelier's principle, the equilibrium will shift away from that in order to reestablish equilibrium. So if you add heat to an exothermic reaction, this will decrease the value of K. If you remove heat of an exothermic reaction, this will increase the value of K. So here we have that example specifically, that's why I had to write it out. So here we have an exothermic reaction. It's giving off heat. This is exo. So heat is a product. And let's say we remove that heat. We're taking it away, right? So this is overall decreasing. In order to respond to that change, what is going to happen is that the reaction will shift this way, because think of it like you're siphoning away one of the products. So think of it like, okay, I'm taking away this heat, taking it away, taking it away. In order to reestablish that equilibrium, we think of it like a product, so it's going to shift that way. Think of it like also like a bowl of candy, and somebody keeps eating all this candy out of the bowl, so you have to keep adding candy to the bowl. I don't know why I'm thinking of candy, maybe because it's October 1st and spooky season and Halloween. But think of that, like you want this bowl to be full of candy, but somebody keeps eating it, so you keep adding candy to it. So same idea here. Overall, this will increase the K value. And then for the opposite, an endothermic reaction, heat is considered like a reactant. It requires heat for this reaction to happen. So if you increase the temperature, this is like adding heat. So according to Le Chateliers Principle, the equilibrium will shift away from that added heat in order to reestablish that equilibrium. So let's say you add heat to an endothermic reaction. This will increase the value of K. So here we're adding heat. So we're increasing reactants. So in order to respond to that change, we will shift to the right to produce more products. This will increase the value of K. Here we have that same reaction we were just looking at, this endothermic reaction that requires heat. So here we have this reaction at a lower temperature. So overall N2O4 is favored, because if the temperature's low, that means that you have to shift this way in order to respond to that change and reestablish equilibrium. On this other panel, we see that it is a higher temperature. It's at 26 degrees versus negative 75. I know that's really small. Yeah, I think those are the temperatures, or it might be negative 7.5. I'm not sure, but this one's higher. That's all you have to know. And for this side, because it's higher, so I'm going to erase these markings so it can make sense. So on this side, it is higher. We are increasing the amount of heat in order to counteract and deal with that change. The system will shift this way, produce more product. So there is more product being formed. It's favored overall, the reaction to shift to the right whenever you increase the temperature of an endothermic reaction. And then finally, we have catalysts. How do these affect the position of equilibrium? If you remember from the kinetics chapter, catalysts speed up reactions. They do not participate in the reaction. They come out of the reaction exactly as they came in, but they do increase the rate by lowering the activation energy. So they lower the activation energy and makes it go faster overall. What does this do to equilibrium? And the simple answer, and you'll probably be happy, is that they do not affect the position of equilibrium. If something happens faster, that doesn't have anything to do with equilibrium. So here we have two reactions that have the same equilibrium, level, concentration. The catalyzed reaction achieves equilibrium faster. So you see how much faster it gets to this point right here compared to this one. It took long all the way over there until it reaches. So catalyzed reactions happen faster. They reach equilibrium faster, but they do not affect the position of equilibrium. It did not change that equilibrium concentration. So overall, main idea for this is catalysts do not affect the position of equilibrium. They do not affect the equilibrium concentrations.